recording. And yeah, there we go. So welcome to the second week of the course. Thank you for being here. Monday mornings are not the best, I know. But today what we're going to be discussing are map coordinate systems and projections. Actually, the other way around, we're going to be talking about projections and then map coordinate systems. And so on the agenda, we're going to talk about what is a projection and how do projections work. And then we're going to discuss how map makers measure and model the Earth just more generally. We're going to talk a little bit about why all maps are wrong, or kind of why they lie a little bit, which is not to say they're not true, just to say that they're kind of forced to do so. And then we will discuss just some different types of map projections and kind of their principles and how they work. We'll talk a little bit about the floating sheep article that you all read. And then from there, what we're going to discuss is coordinate systems. So a coordinate system is like with the grid, where you like overlay a grid over the Earth onto a map and that type of thing. So that way you can accurately locate people and places and things in space. Before we get moving, does anybody have any questions or anything? So your first lab is due on Wednesday before class at 11 a.m. So if you have any questions about that or need any help, let me know. There is a video demonstration online. And then on Friday, the second activity is due, and both of those are using Google Earth Pro. So yeah, if you had just, as always, if you have questions or need help about that, I'm pretty flexible and able to meet pretty much whenever outside of class, so long as you just let me know and everything. So, all right. But like always, we'll do a poll first, and I think I was finally able to figure out how to do polls easily. So you should be able to see it now. Okay. All right, now all of you have answered, so I'm going to end the poll. So it looks like most of you have, let's see, I should be able to share. It looks like most of you do have a map. And so I guess for those of you that do have a map, I'm curious what kind of maps you have. So whoever wants to go first.
I have a world map and what is it, like a transit and bike route map for Bloomington.
Nice. What other maps do you all have? Do you all just have like world maps, or?
I'm pretty into soccer, and I have a map of Europe, and it like pinpoints where all the different soccer teams are in each country.
Nice, that's a cool one. John, I saw that you were unmuting. What kind of map do you have?
Well, I have a couple of globes. I have two globes. One of them is like a modern globe, and then I have a globe from like the 1940s. So
Nice, very cool. I do have a map as well, although it's actually a very recent acquisition, and I never had a map before. That's a little, it's like a 3D topographic map of the United States with satellite imagery, and so then you can kind of like see where mountains are and everything. So I always kind of like to look at like Bloomington in comparison to where I grew up, right outside of Denver, which is very close to the one of the biggest ranges in the U.S., or the biggest range. So yeah, it's very interesting. Really interesting to see how many of you have maps. Actually, this is probably proportionally the highest number of people that have ever said yes, we have maps, that I've had in this class. But yeah, so from there we can kind of get on to the lecture about kind of just what are projections and everything, and how do they work. So have any of you heard of a projection before this class at all? Just out of curiosity. So Hannah, I see you kind of shaking your head. What did you know? What did you know about projections before?
Well, when I hear projection, like anytime I've heard it, it's just kind of like related to an estimate of something, or like a scale version of something.
Yeah, Yeah, actually, so the estimate is something I could see, like a financial projection. So not quite that type of projection, but as far as the estimate of something goes, or the kind of scaling down, that's definitely a big part of it. And you all should have some idea of what projections are after doing the reading and everything as well, which I hope the reading has not been too like onerous for you all, or taken too long or anything. But yeah, so projections are kind of like what you were saying, Hannah. They are essentially it's a way of describing the process of flattening a curved surface onto something that can be placed into a 2D plane of some sort without like, so like if you think about like a piece of paper stretched over a tennis ball, if you like put the tennis ball in the middle and you kind of like fold the paper over it, as long as it doesn't like rip or tear or anything else, like that's a projection. And maps actually have to have projections, so they just modern maps need to have projections. And you can't really even create a map, especially not using GIS or anything, without a projection. So they're really kind of the first step to creating an accurate map. And so, you know, when it comes to projections, what you really need to keep in mind is that projections are a way of going from a 3D surface to a 2D plane. So it's a way of going from like a sphere to a piece of paper, for example. And so there's really a lot of different ways that can work. So how you turn a 3D surface into a 2D one really is, there's a lot of experimentation about the best way to do that. And so the goal of a cartographer, based upon whatever type of map they're trying to make, that's how they choose the projection. And sometimes, you know, I've had to do this, and other people who make maps have to do this. Sometimes you have to create your own projection just based upon whatever your study area is. And so like a map projection that's really good for one city, for example, might not be very good for like the entire country, you know, like a map, like I made a projection that was specifically for Denver, Colorado. And so like it was really made in that way to make it as accurate as possible. But we'll kind of get into the mechanics of that in a bit. And so there's a lot of different types of projections. Some of them are local, like the one I was saying I made for Denver. Some of them are global. Some are somewhat in between and show regions. So there are projections that are like from like Indiana to Ohio, like that type of projection. And not every projection is useful for every purpose. So the purpose of a projection kind of depends on what kind of map you're trying to make. And so where one projection might be really good because it maybe maintains the shape of a place, other projections might not be as good for maintaining shape. You know, they might make a shape look inaccurate or different than it actually is. So you really just have to keep that in mind, that when we're talking about projections, we're not just talking about like the process of creating this 2D plane, but we're also talking about a variety of different types of projections. And so the most famous projection, which we kind of talked about a little bit last class, was made by this guy, Gerardus Mercator, who was like a Flemish, Belgian geographer and cartographer in the 16th century. He's alive from roughly like 1510 to 1590 or somewhere around then. And unlike a lot of his contemporaries, he was from a really poor family. And so he was actually only able to attend school and stuff based upon the support of some wealthy patrons. That's how it worked at that time. And by the mid 1530s, he was really like one of the most well-known cartographers in Europe. And he was really well known for this globe that he created right here, that basically showed the latest geographical discoveries or conquests, probably more accurately, in the world, particularly like the Americas. And so this globe is really what kind of made him famous and where he was able to gain wealth. So it was kind of an early version of mass production. And he produced a ton of these globes and he sold them for super high prices to wealthy people. And so that's what allowed him to become just a full-time cartographer. He was also like a professor. So he was probably teaching, a lot of times cartographers and geographers taught mathematics at that time. So he was teaching math and everything. What's kind of interesting about him in comparison to a lot of his contemporaries as well is that he didn't really travel at all. Actually, he spent most of his life in Flanders and in the Netherlands and Belgium. And so the way that he created his maps was he actually combined the maps and other cartographic knowledge from the other people's books and their maps. And he would kind of change them and combine them based upon the latest research that was coming out. So his first world map was produced in 1538, which kind of made him even more famous. And eventually he was making maps for the Holy Roman Emperor at that time. And this kind of made him not just like really well known among like, you know, cartographers or people that were interested in it, or government officials at the time, but also it made him like the best-selling cartographer of the 16th century. And so he was just like really, really well known even outside of that, where it's like his first atlas that he created. So he actually is the person who coined the term atlas. His first atlas was printed in 1570, and by the time he died in 1595, it had gone through something like 6 or 7 printings, which today doesn't sound like that much, but at that time that was like a ton. It's kind of like unheard of to have that many printings. And I guess outside of his work as a cartographer, he's also kind of well known for having been persecuted by the Catholic Inquisition. And he was actually like held prisoner for a long time and was a fugitive for a bit. And then after he escaped, he kind of got back into creating maps and doing professional cartography, and was rehired by the Holy Roman Emperor and some others to make navigational instruments, so globes, kind of like John was talking about, as well as compasses and astrolabes and other stuff. But what he is most well remembered for today is the world map that he created in 1569, which he called basically we just call it like the map of the world. It had a very long Latin name, like kind of all of them do these days. And the projection that he created in that map is what he is really, really well known for and remembered for today. And so that projection is known as the Mercator projection today. And it has, let's see, I'll pull it up actually. So it has a few different kind of aspects to it. So this is that first world map that he had created. That make it a lot different than other projections, or at least projections of the time. To start off with, it actually uses like straight lines. So you can see all these lines kind of going through here to show direction. And so actually any straight line in here accurately represents the direction that it's going in. And so if you see these lines that are going from east to west, those are very accurate. Like if you're going along that line, in reality, you will be going east to west. Another thing about it is that near the equator, it's very, very accurate and there's no distortion. So the distance is entirely correct. It maintains shape, it maintains angles, it maintains directions. But the main thing that people really think about today when it comes to the Mercator map is that the further away you get from the equator, the more and more distorted different places come. And specifically, places get larger and larger outside of the equator. So his audience, we'll go back to the pictures in just a sec, but his audience for this map was, well, I guess we should say today, the audience for this map is basically everybody. So this projection is the most commonly used map in the world. It's like totally dominant. Everyone in this room has seen a Mercator projection before, not just in this class, but even before you were in this class. They're in classrooms, maybe not quite as much anymore, but they definitely were, at least when I was like younger. Even when I was in high school, it was a Mercator projection. They're in magazines and newspapers. If you see a world map, typically that map is going to be a Mercator projection. People are getting better with it though. So like the Washington Post doesn't use that anymore, for example. Google Maps uses a version of the Mercator, as does Apple Maps and Waze and these other navigation apps. And so it's very, very common today. But when Mercator first made this map, it was actually not really it was not made for a broad audience. So he had like every cartographer, he had a really specific goal. And his goal with this map was to help sailors. So there are very small group of people, and you can kind of see that. So the reason that these lines are accurate to direction when you're going these parallels is because for sea navigation, this is a really useful map. because of it's maintaining those straight lines and directions. So sailors, when they use it, can have an accurate idea of what direction they're going in and more easily find where they are. And then eventually kind of what ended up happening was this map just like proliferated over time. And so then it became more and more popular when really the initial use of it was not meant for anything other than sea navigation. There are some histories that people have written about how this map became so common. I'm not quite as familiar with a lot of those histories, but there are certain people that would say that a big part of why these maps became common is because they make Europe and other places, Western places, appear much larger than they actually are, and that makes them appear a lot more important than they are. I'm amenable to that explanation, but I just can't really speak too deeply to it. But what I can say is that one thing with the Mercator map is that it's really just accurate. It's very, very accurate for that specific purpose. And so today it's actually often misused for projections or for showing the world. Really, there should be other types of maps that are used for showing the world. This is not the best way to do it. So that's kind of a brief intro to the Mercator projection. It's not the last time we're going to talk about it, but it is kind of just a way of thinking about it. Before I just move on, does anyone have any like questions or comments or anything about this?
I have a question.
Yeah.
Let me see if I can figure out how to phrase this. Is there some reason I feel like I never see like a collection of maps to make up a world map, but wouldn't it be more accurate to have in pieces? Does that make sense? Like, is that something that people use? Like you have something kind of large, but then, I mean, is that just not like useful for the general public? Is that the issue?
Yeah, so there are people that do that. I would say it's like not that common. Partially just because like world maps sometimes seem very common when you're like looking at like a newspaper or a magazine or whatever. But really like cartographers don't tend to make that many world maps for the most part. Just because they're kind of like limited in what they can do and what they can show. Like they tend to be a good reference type thing. But there are versions of what you're saying, like these different kind of stitched together maps that have like different projections that are more accurate. So we're going to talk about a coordinate system later on that's called the universal transverse Mercator, which is a version of the Mercator map that's kind of accounts for that better, where it's like splits the world into like 17, I think it's 17, maybe it's 16, 16 or 17 different like zones that are going from north to south basically, and then it kind of is able to more accurately depict the world in that way. But even that, there's just really not that many things that you can do. You can stitch them together. There was a very famous project, which we won't get into today, but is a really interesting thing that the US did in between World War I and World War II, where they tried to do something similar, where they tried to make a giant scale map of South America, and they were planning to do it for every region in the earth, every continent, which just ended up being like a total failure because the scale of it was like 1 inch on that map equaled something like 5 feet in the world, or 10 feet or 20 feet. So what it ended up happening was that map got literally so big that you couldn't even like use it in any way because it took up entire buildings and stuff. So that's something similar I can kind of think of, like stitching these maps together at a smaller scale. Any other questions that you all have? Okay, so yeah, so this is kind of the Mercator. You can actually see these. So just to go back to the sailing aspect, like you could see all these lines. Like these lines, basically, they're not the shortest distance for sailors, but what they do show is it's just accurate. You know where you're going, where it might take a little longer, but you know you're not going to get lost so long as you follow these latitude, longitude lines right here. And then we will real quick watch this video. Can you all hear that? Okay, great. I'm going to mute myself for just a minute.
All right, here we go. If I want to turn this globe into a flat map, I'm gonna have to cut it open. In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat. And that right there is the eternal dilemma of map makers. The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder surface. Unroll the cylinder and you have a flat rectangular map. But you could also project the globe onto other objects, and the math used by map makers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator projection. If you're American, you probably studied this map in school. It's also the projection that Google Maps uses. The Mercator projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator projection. But the original purpose of the Mercator projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points. If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. But that created some other problems. Where the Mercator fails is its representation of size. Look at the size of Africa as compared to Greenland. On the Mercator map, they look about the same size. But if you look at a globe for Greenland's true size, you'll see that it's way smaller than Africa. By a factor of 14, in fact. If we put a bunch of dots onto the globe that are all the same size, and then project that onto the Mercator map, we will end up with this. The circles retain their round shape, but are enlarged as they get closer to the poles. One modern critique of this is that the distortion perpetuates imperialist attitude of European domination over the southern hemisphere.
The Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World. Really?
So if you want to see a map that more accurately displays land area, you can use the Gall-Peters projection. This is called an equal area map. Look at Greenland and Africa now. The size comparison is accurate, much better than the Mercator. But it's obvious now that the country shapes are totally distorted. Here are those dots again so that we can see how the projection preserves area while totally distorting shape. Something happened in the late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. Map projection choices became less about navigational imperatives and more about aesthetic, design, and presentation. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up. But on a world map scale, cartographers rarely use the Mercator. Most modern cartographers have settled on a variety of non-rectangular projections that split the difference between distorting either size or shape. In 1998, the National Geographic Society adopted the Winkle triple projection because of its pleasant balance between size and shape accuracy. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of projections. And just remember, there's no right answer. If you yourself
Just a nice video. I think it just like has a very great explanation of how projections work and kind of what some of their issues are. Anything surprising in that video to any of you, or anything that really kind of stood out? So, I mean, one thing, I guess, going back to Amy's question about different world maps and everything, what they were saying, the reason that Google Maps and these other navigation services use the Mercator is just because Mercator is good for navigation at a small scale. The problem really comes from when you try to map the entire world using the Mercator projection. That's really where a lot of the inaccuracies and distortions come from. But when you're using it just at like the street level or whatever, that's perfect. You know, it's a kind of exactly what you need for that purpose. But yeah, so we can actually kind of go forward and look at a few different types of projections as well, or some other pretty common ones. They mentioned a few. So here's just like a modern version of the Mercator, like we were talking about. And then this is the Gall-Peters. So they kind of went over a few of these in that video, but so this is the Gall-Peters projection. And what this projection does is well, what do you think is distorted? What do you think is distorted on this projection, actually? Why don't I put this question to you all?
Things seem maybe compressed from north to south, largely.
Yeah, definitely. So this projection is trying to keep the area equal, and because it's trying to keep the area equal, what it distorts is the shape of the places. And so these are more accurate demonstrations of how large and how much area each of these continents cover. Where it's like Africa right here is like showing how big Africa actually is as a continent in comparison to somewhere like Greenland, which is often looks like the same size. But as a result of doing that, the weakness is that it kind of sacrifices that shape accuracy. So we'll talk about distortions even more, but every map has some sort of distortion. But what the distortion is kind of depends on what the goal of that map is. This is another one. This is called the Robinson projection. It was created by this guy, Arthur Robinson, in the 1960s. He's kind of like one of the founders of like modern cartography, starting in like the 20th century. And so he tried to make a map that was as visually appealing as possible, but also he was trying to maintain shape without it being too distorted in terms of size and everything. He was kind of trying to make a map that minimized all possible distortions of any kind. And so this map is like both pretty accurate in a lot of ways when it comes to like the shape of places. There are also certain distortions that come with it though, like some places actually might be still too large on this, for example, or the distance might not be preserved. Direction is definitely not preserved in this, where if you're using this map to navigate, it would not be particularly helpful for that purpose. And this is the last one that they had shown, the Winkle triple, which was kind of adopted by the National Geographic Society as their official map in the late 1990s. And the thing about this map is that this map is working to basically get rid of 3 different distortions. And so it gets rid of area distortion, direction distortion, and distance distortion. But as a result, it still is distorting the shape of certain places. And so if you kind of you can kind of see it right here actually with South Asia going down here, where South Asia is actually like especially kind of near the tip of the Indian Ocean, is a lot thicker than it actually is. Like the shape of it is actually a bit thinner in reality. And so that's kind of what this is doing. But as far as a world map goes, I mean, this is a really good example of a world map and how to use a world map, since it does preserve a lot of these things. And I think if I'm remembering correctly, I think this one is actually kind of the map that's starting to replace the Mercator, like in classrooms and on and in journalistic maps and that type of stuff. So this map is very strange looking. It's called the orthograph. And so this is, as far as I'm aware, and I don't think anybody's come up with anything more accurate yet. This is the most accurate map in existence. It's kind of interesting. It has like a lot going on with it. So the guy who created it was this Japanese architect named Hajime Narukawa. And what he did was he actually made this projection in 1999. And how he did it was he got a globe, and then he divided the globe into 96 triangles of equal size that when they all come together would be the globe again. And then what he did was he projected all of those triangles. So do you remember in the video, there's the part where he has the globe and it's surrounded by this giant cylinder, and then it's kind of projecting from the cylinder, from the earth, from the globe onto the cylinder, and that's kind of how the projection is created. So this guy did that, but he did it with like a tetrahedron. So if any of you have ever played Dungeons and Dragons, a tetrahedron is the little dice that you use. It's like 20-sided or whatever. And basically what he was doing with that, so instead of using a cylinder, he's using a tetrahedron because it would maintain the proportions of land and water, but also it would kind of help the map unfold into like a really kind of perfect rectangle. And then he actually kind of like, he's even said that you actually could even improve the accuracy even more on this if you were to increase the number of triangles when you're doing this. So he used 96, but you could kind of continue going from there. And so what this map is doing is it's really realistically representing all of the oceans and continents, even Antarctica. So Antarctica is actually oftentimes kind of ignored in maps. That's why it appears as at the bottom like a little flat strip of land, despite the fact that it's actually huge, and it doesn't look like that at all. And another thing kind of to look at this is like, basically everything in here is, there's very little distortion. There's a little bit of shape distortion, especially if you're looking here like at Brazil, for example. But for the most part, it's pretty accurate. And another thing that's really kind of cool about it is this map actually can fold up into a 3-dimensional globe. I don't know of any other projections that do that, but that's kind of what makes it particularly accurate. You don't really see it very often either, because it is, I mean, is this map like a little off-putting to any of you? Like, does it look kind of a little strange? I mean, I could say it's like a little strange in the sense of last class we were talking about what is centered in maps. And so like we were talking about how Jerusalem is centered, for example, or there was that one map of New Zealand that we're using New Zealand as kind of the center of the world. This map is just kind of a little off-putting because what's centered, or at least off-putting to me, because what's a little centered in here is the ocean. And I think that was kind of the main purpose. And I should say, actually, there are projections that are specifically made for the ocean and nothing else. And so people also do that. You know, it's not just about land surfaces. So if you go to this, I'm going to pull up this website real quick. If you go to this website right here, it's really pretty cool. It has like hundreds of different projections on it that you can go through. So I'll show you the projection that I tend to use in a lot of the maps that I make, which is called the Albers equal area conic projection. So it uses like a cone to project, and then it basically is able to keep area mostly correct. And it's kind of best for like places like the US that are like these long land masses going from east to west. So this is the one that I often use, but you know, there's really a lot of these different ones. You could go to the cube. So this cube one this is another projection of the world. Let's see. I don't even know a lot of these actually. There's so many. This projection right here is literally just a projection made for the Czech Republic, and it uses like a cone as well to do that projection. Let's see. Yeah, so there's like a lot of these, and this is like barely any of them. This is like so few of them actually, but yeah. So these are, you can go to this website if you're kind of interested in these and seeing other projections and stuff, but yeah, so now we can kind of get into the more specific mechanics of map projections. So there are 3 primary steps to creating a map projection. The first one is deciding on what shape you're going to model the Earth as. So typically, you need to figure out how you're modeling the 3D surface of the Earth, essentially. So a lot of projections work under the assumption that the Earth is a perfect sphere, like this right here. And so therefore, they'll model it as such. In reality, the Earth is actually closer to this or closer to an oblate spheroid where the poles of it are really inwards and then it kind of goes out a lot more, where basically the middle of the Earth is a lot larger than the top and bottom. So it's kind of closer to this. I think in reality, the Earth is actually more in between these 2 figures. But which way you decide to model the Earth and whether you decide to talk about the Earth as a spherical 3D surface or an oblate spheroid or an ellipsoid or anything else, it changes how it's projected. So when we saw that video and the guy was, projecting onto that cylinder using that globe was a perfect sphere. And so that really changes how those areas are coming out. Whereas if he was to be using a globe that looked more like this, it would look a lot different. And then from there, what you're going to do is you will turn those 3D coordinates from the Earth that you get into 2D ones. And so that's what we call a coordinate system. So basically what you want to do is you want to turn it from these latitude longitude lines that are right here onto like a straight grid, kind of like what's used on the Mercator map that had used east to north degrees lines. And then from there, so this is kind of, I think, Hannah, what you were saying earlier, you reduce the scale. And so that's the last step of projection. So a map, the actual scale of Earth would just be like enormous and totally unusable. Kind of like that map of South America I was talking about that took so long to create and wasn't even usable in the end. And by the time it was finished, it was already totally inaccurate because it took like 30 years to make or something. So map projections are always used to make the world smaller than it actually is, partially because it's practical, partially because it just wouldn't even be possible to use the map otherwise. But now how the scale of that map is reduced depends on the projection. So there's not just a single way of reducing scale. You can reduce scale in a variety of ways. But one thing to really keep in mind when it comes to map projections is just that no matter what you do, map projections are always going to lose some data or some like data quality, so that no map is like an entirely accurate representation of the world. And maps are accurate, but they always have some inaccuracies to them because that's just the nature of putting this 3D surface onto a 2D plane. And so representations of the world as 2D kind of just like basically lead to that happening. It's just that maps just can't show the complexity of the 3D world, not entirely at least, although we can get close. So globes are a really good way of getting pretty close to that. I think globes are probably by far the most accurate thing that you can use just because they more accurately mimic the actual shape of the Earth and the surface of the Earth. But yeah, so we can kind of get into more of the intricacies of how we're doing those steps. So first off, we're always going to start with a model of the globe. And so in this example right here, the globe is this perfect sphere, but it could, like we've kind of discussed earlier, it could be a variety of different shapes. So spherical models like this tend to be used at smaller scales, whereas those spheroids that we were talking about that were more longer and oblate, those tend to be used at much larger scales. They tend to be a lot more accurate in that way. And so this is part of what we're talking about when we say it kind of depends how a projection works, kind of depends on what the goal of the map maker is. If the goal of the map maker is to create a world projection, then it's probably going to be better that they don't use a sphere and they use more of an ellipsoid. But if they want to just maybe make a projection of just the United States, then it would be a lot more accurate for them to use something like this. And then from there, once you have chosen your kind of globe and what shape it's in, you need to figure out what the center of that projection is going to be. So this is mostly dependent on that shape, but essentially what it does when you choose the center of the projection, like right here, is it determines how the map you make will be laid out and where it's going to touch that surface, which we'll get into in a little bit, how that kind of works. But and then once you've done this, you place a surface. The main ones that people tend to choose are planes, cones, and cylinders, which we'll talk about in a bit. So you place that surface over your globe and then you wrap it around. And so when we're talking about like a projection surface, what we mean is anything that can be wrapped around a globe without ripping or tearing or in any other ways kind of not working. And so from there, your globe is going to touch that surface in a way that is particular to the surface of the shape that you've chosen of the globe. And then this is where we get the flat map from. So I think that one thing I like about that video I was showing is that that video has a really good representation of how that's working, right? Where it's like you're literally wherever that map is touching, that's going right onto that surface. And that's how those land masses are formed. And so what you'll do is you overlay grids on both the surface itself right here, and then on a flat piece of paper. And then what you can see is where those grids touch each other shows the transformation from a 3D globe to a map, right? So if you're looking right here at North America, you could see that that would be kind of like right here, for example. And the difference between projections is that they have different grids that touch at different places. And so grid lines are not always straight like this. Sometimes they actually curve depending on the curvature of the Earth. And so that's going to kind of change how they're touching the Earth and how the Earth is being represented on that flat map. Does that all make sense to you all? Do you have any, like, is there anything that's not clear about that I can clarify or anything? Sorry, I know this is not the most interesting subject, but it's really pretty important to understand mapping and everything. Okay, so from there, there are really like three major factors in projection. So there are projection surfaces. So we've kind of already discussed that, which is how we're modeling the Earth and how the Earth is shaped, which kind of determines where the surface of the map will, the surface of that map will touch. And then there's tangencies. Tangencies are basically the exact point where the projection surface is touching the globe. And so at tangencies, there's not any distortion. So if you look at actually in a Mercator map, the tangency is the equator, which is touching that, and there's no distortion at the equator on a Mercator map. It's totally accurate. The different surfaces have different tangents. But yeah, we'll get into projection surfaces first. So these are the three primary projection surfaces that are used to create a map. And so what you really imagine that like these shapes wrapping around the surface of the Earth, that line of contact between them is the tangency. So a plane, for example, right here, this example has just one point of tangency, which is a little point. This cone has a line going around it up here, which that's like a tangency. And then this cylinder, this is the Mercator projection, is kind of wrapping around the Earth, and that's like its tangency. And so really, we'll kind of look at this, but what you want to do with the planar surface right here is you want to imagine it folding downwards to cover the rest of the Earth. And then when you unfold it, if there was like ink on it, that's what would be that planar map. It's kind of the same deal with this. Planars are not that common, actually. They tend to be more common if you're like mapping the North Pole or the South Pole or something like that, but they don't tend to be that common generally. Conic surfaces and cylinders are a lot more common. So cones are typically used for east-west orientation maps. So that map I was showing you all that I really like, the Albers equal area, that one is a conic map. And the reason it's good is because it's really accurate at showing the United States and how it kind of shifts from east to west. But they're also used for just like regional maps generally, or maps of a single hemisphere. And they're really, really good for visualizing like weather and climate and stuff. So most climate and weather maps you see are conic, use a conic projection surface. And then a cylindrical surface typically can have one or two points of contact. So this one has one point of contact, but sometimes they actually have two lines, which we'll talk about in a second. But the thing with cylinders is that their coordinate lines are straight, they're equally spaced, they're at right angles. They're pretty consistent when it comes to scale. So their scale and size doesn't tend to have a lot of distortion, or at least not the same types of distortion as some other types of maps. And they tend to be really good for world maps and comparing different latitudes with each other, although they have some issues as well, like the Mercator is a cylinder map that has a lot of issues at the world scale. So it kind of just depends. So this is what a planar map looks like. So when we were, you had that over there, this is kind of what they look like. These aren't that common. So the azimuthal equidistant projection, this one totally maintains distance accurately, but shape and other stuff are kind of sacrificed in doing that. And at the center of it is the North Pole. So the North Pole, that is like the tangent right there. This is what a conic projection looks like of the world. So this is the equidistant conic projection. So this one is also kind of maintaining distance, but it's also trying to maintain shape more accurately as well, and a couple other things. And you kind of imagine it being a cone. So if you just like imagine rolling this up, where this part will be really thin and this part's going to be really a lot larger. So that's kind of how a conic projection works. And then this is a cylinder. So this one is different than the Mercator map that we were looking at, but it's basically showing equal area projections. It looks kind of similar to the map we were looking at earlier, the Gall-Peters one. And so these are kind of the three main projection surfaces, but there are other ones, like that one guy used a tetrahedron as his surface. So it really, there's a lot of ways that you can do it. Now, as far as tangents go, there are really two kinds of tangents. The first one is called a point tangent. And so a point tangent is where a tangent that touches the sphere, but only at a single spot. And so what it means is that on these types of maps, there's really only a small area that's undistorted. So the tangent right here is at the North Pole, and it's right in the center. Right there and in that area is totally accurate. No distortion of any kind. But then as you kind of move down and move further down this line, you're going to see that it becomes less and less accurate and it's more distorted. So that's one type of tangent line or tangent. And then the second type, which is more common, is called the tangent lines. And so tangent lines, essentially, they touch the surface at the multiple segments, and that makes them kind of a line that's going around the sphere. And so in using these tangents, there's a lot more areas that are undistorted that kind of go around the parallels on the globe. And there are a lot of different line tangent projections. So actually line tangents are a lot more common in projections. And they kind of differ based upon which grid line on the Earth they're touching and how many lines. So if we're looking at this projection right here, for example, the line tangent is right at the equator. This is the Mercator. But if you look at this one, the tangent is actually a lot more further north. So that really does change how the projection turns out and what its distortions are, right? So a conic projection tends to have a tangent that's not at the equator and tends to be closer to the North Pole or the South Pole, depending on how you do it. But tangents can also have multiple parallels. So there are a lot of projections that actually have multiple tangents. And when a projection has multiple tangents, it's known as a secant. You don't have to know that term, but just in case you're curious, that's what that's called. And basically what that means is that if it touches multiple lines, there's a greater area that's distorted. So if you look at these projections right here, for example, they have two tangents. They have one tangent here and one tangent here on this conic projection, or on this cylindrical projection. There's a tangent right here just above the equator, and there's a tangent here just below the equator. And so that area in between those two lines is totally undistorted. And that's kind of what makes them a lot more common to use multiple tangents or secants versus that single one. Yeah, so basically these projections are more common just because they make the Earth appear as it actually is in a lot more areas than this one's singular tangents can. Are tangents making sense to everybody else? Does that kind of track? Okay. So then from there, what we can do, so this is the Albers equal area, the one I was talking about. Then there's the Gauss-Peters and the azimuthal. We've looked at all these already, so I will kind of keep moving on. But then the last thing about tangents, and then I will stop saying that word, because the more you say it, the less it sounds like a word. Is just that there's no distortion really around them. So this is kind of a really nice graphic for showing that. So if you look at this cylindrical tangent right here, you could see that the line right here is like there's no distortion, but then as you get further, they get smaller. So that really, you want to think about distortion in terms of the further you get away from a tangent, the more distorted something becomes. And so where that tangent is determines where distortions are going to happen. And like I was saying before, every projection distorts a map in some way. So there's no perfect representation of the Earth. I really like this graphic. I think it's just like a really good way of showing distortion. So, you know, on the top left hand, you can see that this is just like someone's head. But then if you put an orthographic projection here, it makes it look a lot really distorted. The Mercator projection makes the forehead look giant and the chin and everything also. And so there are 4 kinds of distortion that are present in all projections, but it varies how much of each distortion there is. So I think you can remember this by this little saying, those damn ads. So area, some projections make an area appear larger or smaller than they actually are, like with the Mercator. Direction, so some projections make it so that the direction on the map is actually not really accurate in terms of when you're using it. Distance, I think that's pretty explanatory, and shape. So we were kind of commenting on some of the shapes on maps earlier that look different. So every map has these are the 4 types of distortions that happen with maps and with every kind of map. The extent to which each one has a different, there's kind of a combination of distortions depending on the type of map. Some maps might not have any distortion for area, but they'll have distortion for direction, or they won't have any distortion for shape, but they will for distance, and so on. And so just like every time you're looking at a map, just keep these in mind, right? Ads, area, direction, distance, and shape. They will all have some type of distortion, and if you look close enough, you'll be able to find it. So now what we're going to do is I'm actually going to stop sharing I'm going to pause the recording, and all right, now we can kind of continue on with the lecture. I think we're about to have a break coming up, which is good. But we'll just check out this graphic real quick. Let me reshare my screen one more time. Okay, yeah, so check out this graphic of the Mercator stuff. So this is similar to the true size of. This is showing just like keeping them all in the position that they're at, but actually showing each of the countries as they are. And so on this graphic, I just marked where the tangent is in this Mercator projection, just so you all can visualize that. And so you can see, right, how like Brazil or Liberia or a variety, or Zimbabwe or a variety of these other countries don't really change at all when you actually change the true size, right? But then the US gets so much smaller. Greenland, like the Greenland example is so wild. Alaska, Russia, all these places are actually much, much smaller than they appear on the map. And so this is just like a really cool example of that. And now why don't we talk one more time real quick, and then we will take a break after this, but let's talk about this floating sheep article that you all should have read. I'm going to stop sharing my screen. So I'm hoping that most of you read this, or at least read as much as you could of this article. Would anyone be willing to kind of give me a summary of it, or maybe like some of the key points that you kind of got out of it? Also say maybe whether you enjoyed it or not after reading it.
I definitely liked the writing style. It was easy and pleasant, kind of funny to read. I enjoyed the humor.
Yeah, a lot of those people are cool. So some of them they have a lot of connections to people here at IU. And one of them actually came here and was a GIS Day speaker last year as well. Jack, but I don't remember if Jack was part of this project exactly. So what would you all say, like, kind of some of the main points of this article were? Like, what did you get out of it?
I guess maybe I'm having trouble expressing any main points because it seemed like it was more opening up a conversation than laying out a guideline, or like almost like laying out guidelines for a conversation.
I mean, that's good too. So like, what conversation do you think they're starting?
Really just about like where there can and can't be accuracy, maybe, and when it is when it's important that information is being falsified, maybe.
Yeah.
Part of it. Whether sort of the deluge of information that the internet kind of dumps onto mapping it creates greater accuracy, or
the internet thing is kind of, for me, the biggest part of this article, actually, about how, like, on the one hand, the internet's amazing because it allows more people to be cartographers than was ever possible before. But on the other hand, it leads to a lot of really, really bad maps that are really inaccurate and really poorly made. But I mean, another thing, I mean, did this article at least kind of feel familiar to a lot of you after our lectures last week and stuff that we were discussing? And so, like, another thing in this article that I really enjoy, and I think is worthwhile, is how they're kind of talking about the ways that maps are subjective. And so maps have their own histories, and those histories are kind of created by the cultural, historical, and social context where they're created. So we talked about Jerusalem a lot last week, and they talked about Jerusalem some in this article. So you can really think about it in that way. But one thing I also so they do have kind of at the end of the article, they have their 6 main points, which are kind of tongue in cheek, but also pretty serious. But another thing that they really bring up in this essay that I like, and I think is actually not really that common in cartography, is that people take maps sometimes too seriously. Like I kind of like how irreverent they are in this article, where they're just like, sometimes it's just fun to make maps that don't mean anything about like sometimes they actually don't have a point, but there might not be causation between 2 variables. But just because there's not causation doesn't mean that there's not these patterns, right? So there might be these other patterns that are present somewhere where why? So they have the one example about, I think it's like zombie brains versus salads or something, and how people would search for that. And so like that in and of itself means nothing. Those have no connection to each other, right? But what it does open up is a new type of question, which is, why is it that this place is searching for zombies whereas this place is searching for salads. Like, what's the distinction between those places that makes that happen? You know, like, not because those variables are connected to each other, but just because there's these other things that are kind of happening that make that happen. But I'm glad that Amy at least liked this article. I don't know if any of you, I don't know if the rest of you like the article. I hope so. I'm really doing my best to not overload you with reading. It's unfortunate that this class is so shortened, which makes that very difficult to do. But we can kind of just discuss a few of these maps from the floating sheet project, and then we can kind of keep moving. So I'm going to reshare my screen. And I'm actually going to go for some maps that you didn't see in this article. So these should be new to you, or at least most of them should be new. So if you look at this map, you know, I think this thing is kind of nice because showing there's not actually like a causal relationship between a lot of this, especially because it's just showing tweets that mention beer or church and mapping out where those were done. But it is kind of interesting to see this geographic pattern. The pattern itself is interesting. There might not be a relationship between beer or church or tweets about beer and church, but there is a pattern here, right? You can see where areas in the southeastern US, there's a lot more tweets about church than there is beer. Whereas if you go to up to Michigan, there's a lot more tweets about beer. Nick, you're from Michigan. Is that surprising to you?
No.
Yeah. Is it surprising to you? Actually, one more question, Nick. Is it surprising to you where in Michigan the most beer tweets are right here?
Not really. I'd say the most populated area in Michigan is definitely the southeast around Detroit. And as you go further west and north, it gets a little bit more scarcely populated. And I think people there will care more about their beer. It's kind of more, you know, forest and wilderness.
That makes sense. Do you have any conception of why these areas in the southeastern part of Michigan are more church? There's a lot more church there.
Yeah, there's the population around Detroit and in the Metro Detroit area is very mixed. There's a lot of, I think there's the largest Arab community outside of the Middle East. And there's also a lot of other small communities that just different religions, but there's a lot of religious beliefs mixed into one area. So I think it'll be a lot more important towards Detroit where it's, you know, like that.
Got it. Thanks, man. So as you can see, that's an example of that, this conversation we just had. This map doesn't show anything, but it does show these different questions. This is the map, you know, of just showing the mentions of bars in the areas in Google Maps and how often there are bars. This is also not the best map, but it's kind of intentionally made to not be great. This is totally unsurprising because this is basically a population map. And so it's kind of showing where things are and where they are not. You know, this part of Colorado right here is basically where everyone lives. Or this is the map we were talking about, the zombies, the more brains, the more salads tweet, you know, kind of joking, but also pretty funny. Bronies and juggalos. Do any of you know what bronies are or juggalos? So bronies are the adult fan base that's typically middle-aged men who love My Little Pony, and they're very, very serious about My Little Pony. There's a very funny Bob's Burgers episode where they make fun of it, if any of you watch that show. Juggalos are just these fans. What'd you say?
Aren't juggalos like Insane Clown Posse fans?
Yeah, yes, they're the Insane Clown Posse for people. This will not be the last time we talk about juggalos in this class. They will come up again. Also, their music, surprisingly wholesome, actually. I don't know if you've ever listened to it. It's like about like chilling with your friends and being homies and stuff. It's kind of nice. But yeah, so this is just like I just think this map is hilarious, basically. Like, I actually don't really even have anything else to say about it, but it is kind of interesting to see the fact that it's just like, there's just way more juggalos in the US than there are bronies, you know, and especially there's a lot of juggalos in this area of the Midwest. In particular, they love Faygo. If any of you have had Faygo, that drink, I think it's totally gross, but yeah, and here's another one, you know, comparing juggalos to polar bears and stuff, and I don't know what's up with these few areas that have more polar bears than juggalos. That's shocking to me that that would even be happening, especially in California. Yeah,
Wait,
you know, tweets about.
is
Oh yeah,
is polar bears code for something that I don't know, or are they just straight up mean polar bears?
they just straight up
Okay.
mean polar bears. Yeah. And then this is another map of just the world showing also great projection. This is a very good projection of a map of the world actually. It's kind of like curved and everything on the sides, but this is about like tweets about hobbits versus tweets about Chuck Norris. It turns out that New Zealand does in fact have more tweets about hobbits than they do about Chuck Norris, which is kind of unsurprising. But so it's already 12:23, so I'm kind of thinking that we could just push through if that's okay with you all instead of taking a break like we normally would. Sorry, I hate to do that. That's my mistake. I was just talking too much, and I think we spent too much time discussing that activity, but I think it was good. And also, you all don't want to hear me talk that long anyway, so us all talking with each other is probably best. But so if that's okay with everyone, we can kind of just keep moving forward. And so now we're going to finish this off by talking about coordinate systems. I would pair coordinate projections and coordinate systems are kind of paired with each other. And what a coordinate system is essentially is it's a grid that helps us find the locations of things in space. And so like that grid is what we refer to as either a geographic coordinate system or a projected coordinate system. So there are two different kinds of coordinate systems, which are GCS, geographic coordinate system, and that is like a coordinate system that is overlaid over the Earth as a sphere or as a globe. And then there is the projected coordinate system, and the projected coordinate system is like the mapped coordinate system of like the 2D grids. So if you want to consider an example, think about grid lines that are overlaid over a globe. So like John was talking about earlier, how he has some globes. John, do either of your globes have grids on them?
Yeah, both of them do.
Okay, so those grids that the globes that John has, those are the geographic coordinate system. And then on that Mercator map that we were looking at that has all the right angles and the latitude and longitude lines, that's a projected coordinate system. Every map has both. Every 2D map has both a geographic coordinate system it's based on and a projected coordinate system that you can see and that it uses. And basically, yeah, so, you know, every projected coordinate system is based upon a geographic coordinate system. And so for the geographic coordinate systems, the way it works is you first divide up the planet based upon these vertical horizontal lines. And so once you overlay that grid, what it'll do is it'll have two different lines that make the grids up. It'll have latitude lines, which are these lines that are going east to west, and it'll have longitude lines, which are going north to south. And so for latitude lines, what they do is they range from -90 to 90 degrees with the 0 located at the equator. So if you go north of the equator, it will increase. And if you go, that number will increase. And if you go south of the equator, that number will decrease into the negatives. So basically north of the equator is positive numbers, south of the equator is negative numbers. And once you actually have that memorized, it makes it really easy to be able to figure out where things are roughly without even having to look at a map or anything else. Because you know that if someone says something is 90 degrees north or 50 degrees north, you know that that's above the equator. So you can have kind of a rough idea. And longitude lines pretty much work in the same way, except they go from 180 to -180 degrees. And they actually meet at the poles. So they meet here, up here at the North Pole, which is 180, and then down here at the South Pole, which is -180. And the middle of them, that 0, is the prime meridian. And so so once you go east, it's the equivalent of the equator. When you go east of the prime meridian, it's positive numbers. And when you go west of the prime meridian, it's negative numbers. And so if we were to say something is 50 degrees north and negative 50 degrees south, then we would know that that's going to be roughly around here, or roughly kind of around here, you know. So we can kind of really figure that out pretty well. Does that all make sense to you all? So I feel like it's really worthwhile to remember just north positive numbers, south negative numbers, east positive numbers, south negative numbers for latitude and longitude lines. And that should make it a lot easier for you all as well, just to, in terms of doing this next activity that's going to be due this week. And then when we talk about meridians and meridian lines, what ends up happening is, so meridians are like that prime meridian going from north to south. That's like the main meridian, but there are a lot of different meridians. And so what we call principal meridians are these meridian lines that are used as reference points for surveying large areas. And so if we look in the US, for example, right here, here's the third principal meridian, and that's like what separates Western Illinois from Eastern Illinois, or the second principal meridian here in Indiana separates Western and Eastern Indiana from each other. And so that's kind of like actually kind of the way that a lot of Midwestern states got their boundaries, was kind of based upon being centered on that principal meridian. So that's just kind of something for you all to keep in mind when it comes to this. Latitude, longitude, meridians, are these all pretty much making sense to most of you? Cool. And always feel free to interrupt me if you have questions. It's totally fine. So we're looking at this map. Let me zoom in a bit. Well, actually, I don't know if I can zoom in. I hope that you can all see it okay on your screens, but this is an example. This is Bloomington, but this is Bloomington on a projected coordinate system. Do you all think you could roughly say where Bryan Park is in terms of these coordinates, and where, say, the sample gates are in terms of these coordinates? So you can see these latitude lines and longitude lines on the X and Y axis. And you don't have to give an exact coordinate or anything, just like roughly, if you could say where it is in terms of north and east degrees.
Would like Bryan Park be like 34 degrees north and 41 degrees east?
Yeah, just about, roughly. Yep, roughly 34 degrees north and 41 degrees east. What about the sample gates? The sample gates are about around here also, in case you aren't familiar with the campus. This is kind of an older map too, so it does look a bit different than it does now. It's fine. I can give you the answer. Roughly, it's not that much of a difference. Oh, Amy, did you have a?
Oh, I was just gonna say, I just can't see them on there. Like
it's totally fine. And this map is older, so it's like kind of unfamiliar in that way as well. It's like roughly 34 degrees north, 43 degrees east, kind of. So you always have, this is just like algebra. It's always X, Y coordinates. So, you know, the X-axis, then the Y-axis. So just if you remember that, latitude is the X-axis and longitude is the Y-axis. So as long as you did algebra in high school, you should have some familiarity with these concepts already. And speaking of, I'm going to make you do some algebra just to kind of get help you get the hang of this. So what would the coordinates be for these points? John?
A would be -3, 4. B would be 4, 1. And then C would be 3, -5.
Yep, exactly. So that's exactly how this works. You know, basically, you want to think about maps and coordinate systems in terms of geometry, not geometry, in terms of like algebra and geometry, like you did in high school or whatever. And so as long as you like pass those classes and kind of have some understanding of that, this really does work in about the same way. And that's kind of how people use maps, especially maps that have like these grids on them, you know? So people use these types of maps all the time, and especially for like their field work that they're doing outside. Environmental scientists use it a lot, that type of stuff. And so as far as projected coordinate systems go, which those were kind of examples of it. Also, you might hear my dog, she just got surgery on Friday and she has a cone and she's being very annoying, but she's fine. Can you go away? So we were talking earlier kind of about these coordinate systems. So basically what we're using is a Cartesian coordinate system. And the Cartesian coordinate system just means we're measuring X and Y. And then the middle of it is split. And then, you know, to the west is negative, to the east is positive, north is positive, south is negative, that type of thing. And it's basically just being overlaid onto this. So this map right here is an example of a projected coordinate system that uses Cartesian coordinates, where it's like the further you go this way, the further you go west, the more negative it becomes. The further you go north, the more positive it becomes, that type of thing. Amy, you were talking earlier, asking about stitching together maps. So this is an example of a map that does this. It's called the Universal Transverse Mercator. It's a very, very common projected coordinate system. I actually misspoke when you were asking earlier. So it does divide the world into 60 north and south zones. And these are the ones for the United States. So the US is 10 through 19. So like when I was in Colorado doing a lot of my research, I would have to use the UTM of 13 for mine. And this is one that most people use. It was first developed roughly in the 1940s. And it was for the US Geological Survey was when they first started making it, which is basically trying to figure out where things were. So each of these zones stretches over 6 longitude lines. And so that's basically how they're able to do it. So total there's 360 because it's a sphere. And then the way that you measure them is actually using these things that are called northings and eastings. It's not that common, northings and eastings. I don't really even use them ever, but they are like, that is the distance and how they measure distance in this projection. A lot of projections use like meters or whatever, or kilometers, for example, but this is northings and eastings. We're going to have a week where we talk about topographic maps and compasses and stuff. And so we'll talk about more about northings and eastings then. And most of them, the grids are kind of like 1,000-meter intervals that separate each grid line roughly. So that's part of why it's so useful. I'm a pretty big proponent of the UTM. UTMs are really helpful when it comes to navigating using a GPS. So like a few years ago, I did some work in the Grand Canyon where I was doing just like some GIS work, just mapping some stuff out. And UTMs were really, really useful when I was mapping it out, because then I could figure out exactly where I was when we tagged a tree for removal or whatever else. The fire department in the Grand Canyon has an interesting policy where basically you only cut down trees if they could create a fire where people are living. And otherwise you kind of just like let the fires burn themselves out over time. And so sometimes those fires will last for months at a time before they actually burn out. And you know, I was going to end this with a activity on coordinate systems, but maybe we can just kind of go do this together real quick instead of putting you all into breakout rooms. So give me just a sec to pull that up. So there's this website, it's called geoplanar.com. GeoPlaner is a really pretty cool website. And so what it does is it'll show you, it'll just kind of keep it just like this. And what we're going to do is up here on the top right, you see there's this little button right here. So that button stands for layers. So you have to think of every map like a layer. The base layer is, it's called a base map. And then basically every layer are these other variables that you stack on top of the map. And that's how you create a map. And so what we're going to do is we are going to change this to OpenStreetMaps. And so OpenStreetMaps is a lot easier to read. And we are going to first, in this UTM box right here, that says 16, we are going to change 16 to 15 right there. And then we're going to click OK. And it's going to kind of change where we're looking. And then in this box, sorry, give me just a sec. And then in this box, what we're going to do is we're going to change it back to 14 now, then 10. And so what this is doing is this is changing the eStigs and it's changing what UTM zone we're in. And so that's why we're moving around, right? So that's where J is, for example. So it kind of does that. And from there, what we're going to do is we are going to change some of these decimal degrees. So let's go in this green box or in this yellow box. Let's change the latitude to 13 or negative 13. Okay. And then we're going to change the longitude to negative 72. Roughly. So now we're in Lima in Peru. But now if we remove the latitude, if we remove the negative from here, it's going to change it. We're going to be right outside of, right kind of in between in the Indian Ocean, between near India. And so this is such a rough example, and I'm actually going to stop sharing my screen, but this is a very rough example of how coordinate systems work, where if you just change that one little thing, like the negative, it's going to move you entirely to a different place. And that is all I have for you all. Real quick, let me bring up what we've got going for tomorrow and for next week, and just some upcoming activities and everything. So I'm going to share my screen one last time. Okay, so for tomorrow, what we're going to be discussing is geospatial data and specifically GIS. So I've kind of offhandedly mentioned GIS a lot in this class so far. And so tomorrow, what we're going to be doing is we're just going to be talking about it. And so you have two short articles to read. Or well, one of them is actually just a chapter in a book, but you have, they're both very short. And basically what they're both going to be doing is they're just going to be introducing you to GIS and the basic concepts of GIS and how it's applied and that type of stuff. As far as your upcoming assignments go, you have two that are due this week. So you have lab 1, which is due this Wednesday, and that's going to be due at 11 a.m. so before class. A few of you have already submitted it, but if you haven't, I would really suggest you kind of get working on that. So that way, if you have any problems, you can email me and we can kind of work it out together more quickly. And that's going to be using Google Earth Pro. And then we have activity 2, which is also going to be using Google Earth Pro to measure distance. And I have like video demonstrations up for both of those. So you'll be able to kind of go through those pretty quick. And then we have a second lab that we're going to discuss tomorrow called about child poverty in Detroit. And what we're going to be doing in that lab essentially is getting you used to the software we're going to use for the rest of the semester. That's called ArcGIS Online. And ArcGIS Online is pretty essential for you to know. And so I think this lab will be a good way of kind of getting you to know that. And it'll be due a week from tomorrow. And I will have a video demonstration of that up soon as well. Yes, that's kind of all I've got for you all. Do you have any questions or anything about the labs or activities? Are those going okay for everybody? Okay, cool. I'm going to stop recording.